we were looking at the limit equaling positive or negative infinity. Agreed? So our y value is positive or negative infinity. Now we're looking at limits at infinity. So we're looking at our x value approaching infinity. We kind of went over these together. Okay? But basically what ends up happening is because my x are approaching positive or negative infinity, we're talking about end behavior of the graph. Yes? So when I'm looking at my ends of the graph, we're looking at as x approaches positive infinity is the right side of the graph. As x approaches negative infinity, we are looking at the left side of the graph. Yes? Which we can represent with infinite limits. So, as x increases or decreases, without bound, f of x approaches some value of L. Yes? So this is the notation we want to use. We want to use our limit notation. Okay? So if I'm talking about this f of x, I have the limit. As x, let's start with positive infinity. We all tend to do better with that. Of my f of x. So 3x squared divided by x squared plus 1. So now let's think. Is my top or my bottom increasing faster? Why? Okay. Ish. We're on the right track. If I'm getting really, really, really big numbers, and I add 1, is that really going to affect that number all that much? No. Okay, so again, this is scratch work. We think this in our head. We don't put an equal sign and put this. We all with me? So this is over to the side. Okay, so if I have 3x squared divided by x squared plus 1, yes? At the end of the day, we said, is that plus 1 really going to affect my really big numbers all that much? No. So we're just going to pretend it's not there. So now, what can I do? I'm going to put an arrow. That doesn't actually equal it. But. So now what can we do if I pretend that the plus 1's not there? Not quite. Just add that fraction. What can I do with that fraction? Reduce what? What do we get? Which is? Yay. So this equals 3. Yes? No? Maybe? And the reason for that is because are my x squared going to be increasing at the same rate? Just the x squared. Are my x squareds increasing at the same rate? Yes. So if they're increasing at the same rate, and we said my plus 1 doesn't really end up affecting it all that much, then the way that my x squareds is increasing basically reduces with each other. Or like y'all like to say, cancels with each other. So we're really just left with a 3. Yes? The other thing that we can compare it to is, if I'm talking about end behavior, and we are getting closer and closer to a number, what am I talking about graphically? What kind? Right, so we're talking about horizontal asymptote. Agreed? So do you all remember, we're not going to use it all that much. We're just calling back for a second. From pre-calc, where we had our horizontal asymptote rules. So if the degree of the top was smaller than the degree of the bottom, the degree of the top was bigger than the degree of the bottom, or if the degree of the top and the degree of the bottom were equal, right? Then remember, we just looked at our leading coefficients, and we got 3. Yes? Do you vaguely remember that? It's been a while. Okay. So like I said, this was us thinking through it. I'm going to show you how to algebraically do it here in just a second. Are you with me? Because this does kind of feel like cheating, I know, because we just got rid of a 1. But I'm going to show you why it actually works like that here in just a second. So, horizontal asymptotes basically are limits at infinity. So, f of x has a horizontal asymptote if as x increases or decreases without bound, f of x approaches some value L. So notationally, we're looking at the limit as x approaches positive infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L, means that we have a horizontal asymptote at y equals L. Are we all with me? So again, she's kind of combining our infinite limit notation with, now we're going to call it a horizontal asymptote. Yes? But again, remember, we are in calculus world now, so if you are asked to describe the behavior of a horizontal asymptote, there needs to be limit notation somewhere on that question. Okay? It's not pre-calc anymore. We're not just comparing degrees. We need to look at what our f of x values are approaching, which means we need to have a limit there. Does that make sense? Okay. Continuing on. So we looked at some of our special trig limits. Yes? We are one more. And actually it has to do with that last one. Okay? So if I'm looking at the limit as x approaches infinity of 1 over x, what does that equal? Yeah, it does, right? So again, I'm thinking I have stuff that's getting infinitely big on bottom, which means that the whole thing would be getting infinitely closer to 0. So this equals 0. Now, if I'm looking at the limit as x approaches negative infinity of 1 over x, what does that equal?
Negative 0.
So, is there a negative 0? No, so it's still just what? 0. Basically, it's just, so if you're thinking about a horizontal asymptote, right, we're thinking about approaching 0 from the top versus approaching 0 from the bottom. So you would be approaching 0 from under the x-axis, but you're still approaching 0, right? So it's still just 0. Are you all with me? Those are going to be helpful in just 1 second. Oh, yeah, these are really important. Oh, and at the end of the day, if my top is like 4, is that going to affect that x on the bottom that much? No. If my top is 100, is that going to affect that number on bottom that much? No. So if it's just some number, I put 1 just for simplicity, but if it's some number over x, and we're looking as x is getting infinitely large, it equals 0. Okay? So, here's one. Similar to like what, we're not going to write it out, but if we thought about, if I raise an infinitely big number to the 4th power, what are we going to get? Really big number. And then I add 5. A little bit bigger, right? Not that much. But then I take the square root of that really big number. Yes? It's going to make it a smaller, really big number, but it's still a really big number. And it's still positive. So this is going towards Positive infinity. So does this have a horizontal asymptote? No, because it's increasing without bound. So sometimes that's why we learn about infinite limits first, because sometimes our limits at infinity equal infinity, and that's okay. Yes? No maybe. All right. Now what's different about this one? So again, if we think about plugging in, we can't actually do it, but think about plugging in our infinity. We have an infinity on top and an infinity on bottom. So it's kind of hard to compare them to see which one's getting bigger faster because they're both linear. Agreed? Yes? Alright, so this is where I said that special limit is going to be helpful. Okay? So we had fractions on both of my special limits. Yes? So we want to turn, right now we have a fraction, but we want to turn the top into a fraction and the bottom into a fraction. So notice that the degree of the top is 1, the degree of the bottom is 1 as well. So we want to multiply, okay, by 1 over whatever the degree of the bottom is. So like in this case, it's x. But what I do to the top, I also have to do to the bottom. That way I'm not actually changing the value. Are we all okay with that? Yes? Again, this is just a setup. What do I need to make sure I include on my second step?
Limit x to infinity?
Yes, have I evaluated my limit yet? No, which means that I have to still put my limit notation. So now, if I apply this to both of those, okay, I have 2x divided by x plus 1 divided by x, and then apply it to both of those on the bottom. Are we all okay that I'm just distributing there? Yes? Okay. Now, what is 2x divided by x? 2. I can't simplify 1 divided by x. Okay. X divided by x is 1. Okay. Now, remember, our limit properties tell us that technically I can look at the limit of the top divided by the limit of the bottom, and because we're adding, I can look at the limits of each of those separately now. We all agree? Now, I'm not going to write all of that out, but we can think about that in our mind. Yes? What did we just say a second ago? That the limit as x goes to infinity of 1 divided by x is 0, right? Because again, these fractions are getting infinitely big on bottom, which means that the whole fraction is going towards 0. So we're just left with the limit as x approaches infinity of 2 over 1. Do I have anything to plug into now? No. So if I have the limit of a constant, it is just the constant, so we get 2. Which is why I told you at the end of the day, adding or subtracting here isn't going to affect it all that much, because really that limit ends up going towards 0. Yes?
Like, if we get a question on a worksheet or like the AP test, like we'll get counted off for just doing like canceling out the ones and then going from 2x divided by x.
Are you putting an equal sign in between?
No.
So then where are you doing that work? If it's just a multiple choice question, you don't have to show work. You're not being graded on your work. If this is a free response question, you would not want to put an equal sign and then just get rid of your ones. Okay? So either you would need to do this, or depending on what the question, if the question said prove or show that the limit is 2, you would need to do this work. If it just said what is the limit, you could just say equals 2. Like you wouldn't have to show any work. Does that make sense? Okay. But you would be counted off if you put equals the limit as x goes to infinity of 2x over x. Those two things are not equal. That's why I said to be careful about scratch work versus equals work. That's a good question. Yes?
How do you know at the beginning to multiply it by 1 over x?
So that's a good question. So I have a rational. Alright, so I have a fraction. Okay? If I have something like an e to the x on top and just an x on bottom, it's easy for me to see my e to the x is getting infinitely larger, right? Much more quicker than my x is. So that would be infinity. Yes? But basically, anytime that I have a rational that just has polynomials on top and bottom, you're going to want to do this. If I have other functions like sines, e to the x's, square roots of x's, like stuff like that, where you can easily decipher which one's getting bigger or faster, right? If the top is getting bigger faster, it's just infinity. If the bottom's getting bigger faster, then it's 0, right? But on ones like this, where it's a little bit harder because I have a polynomial divided by a polynomial, that's where we want to do this thing. Does that make more sense? Yeah. Are we all okay with that? Okay, let's look at another. So what's different about this one? As a cubic, okay. Well, what else?
The degree of the denominator is larger than the degree of the numerator.
Ah, okay. So theoretically, right, my denominator should be getting bigger faster. Agreed? However, if I have a polynomial divided by a polynomial, we can still do the technique that I just showed you, okay? What would we be multiplying by this time, though? We want to multiply by 1 over the biggest degree of the bottom, which is what this time? 3. So it would be x cubed to the top, and 1 over x cubed to the bottom. We're all okay with that? Okay. Which, again, making sure that we put our limit as x goes to infinity. If I multiply x squared by 1 over x cubed, what are we left with? No. X squared times 1 over x cubed. There we go. Okay. And then my second one would be 2 over x squared. Agreed? My denominator would be 1 plus what?
1 over x squared.
Okay. Yes? So again, is on both my x squareds, they're not just x's, but I have a number on top and something that's getting infinitely bigger on bottom. Are those still going towards 0? Yeah. So this fraction goes towards 0, this fraction goes towards 0, this fraction goes towards 0. So we have 0 divided by 1, which is just 0. Which is why if the bottom is getting bigger quicker, we still end up with 0. And this is why. Questions on that? Yes? Where? Here? Because x squared times 1 over x cubed would be x squared divided by x cubed. So 2 of my x's would reduce and we're just left with 1. Other questions? Okay. What's different about these ones? Oh yeah. We have square roots this time. Okay. Which makes it kind of funky. But notice that I also still have x's on bottom. So we can't just think of it like 1 divided by a square root. Okay. So we're going to still do our trick, right? Or our technique is to multiply by the biggest degree of the bottom. But what is the biggest degree of the bottom technically here?
1 over x.
Yeah, so like my degree essentially I have an x squared, but it's inside a radical, so that biggest degree is actually just 1. Are we all with me? So I'm multiplying by 1 over x. Now on the bottom, we're going to multiply by 1 over the square root of x squared. Are we all okay with that? We all agree that those two things are equal. But then in order for it to go inside of my square root here, I need it to be inside of the square root there. So we get the limit as x goes to infinity. On top, do we agree that we get 3 minus 2 divided by x? Yes? Okay. And on bottom now, we're going to have the square root of 2 plus 1 divided by x squared. Yes? Do we all see how I got those values? I'm just distributing. Okay? So this one still still goes towards 0. This one still goes towards 0. So what are we left with?
3 over
That's your answer. Well, okay with that. Yes, no, maybe? Alright, we're going to stop there.